Hello, everyone. Thank you for coming our conversation. My name is Chengming. I am from Washington State University. We are collaborating with Pacific Northwest National Laboratory. Today, I'm going to present our work, CEAZ, Accelerating Parallel I/O via Hardware Algorithm Co-Design, Adaptive Lossy Compression. Then I will talk about why we need lossy compression. Lossy compression will provide high compression ratio, but it will lose some accuracy. Besides, currently data is extremely large. For example, NICs cosmology simulation can generate up to 2.8 terabytes data per simulation. And besides, such large amount of data is often generated in a parallel manner in multiple nodes, on which each holds a proportion of the data, and must need collective communication to dump the entire data to the file system. So, therefore, it is urgent to develop effective data reduction method to reduce the size of data movement. Then I will talk about the storage in the I/O issue. So past a few years, the computer capability is growing very fast, but the storage capability and bandwidth is developing much slowly. So, for example, the LP column is the peak performance, and the SB column shows the storage bandwidth. The peak performance has been developed by more than 100 times, but the storage bandwidth has only gained 10 times from Jaguar supercomputer to the Summit supercomputer. Then I will talk about the dequantization problem. So dequantization is a novel two-phase prediction quantization approach. Our dequantization consists of two steps: pre-quantization and post-quantization. Giving floating point data, we will firstly quantize it based on the user set error band and convert it to integer data. After the pre-quantization, we can calculate its predictor value based on its neighboring value and using Lorenzo predictor. Then the second step, called post-quantization, we will compute the difference between the predicted value and the pre-quantized value. The difference will be compressed by Huffman compression. Then we focus on the FPGA-based compressor. WaveSC is another hardware implementation of SC lossy compression. It adopts wave from memory layout, but it just alleviates the data dependency. Didn't not eliminate. And besides, the wave from memory layout involve rearranging the data before compression. Burst SC is a variant of one-dimension DLP algorithm. DLP can provide high throughput, but it suffers from significantly lower compression ratio compared with original DLP algorithm. And its throughput is 8 gigabytes per second. And such a throughput is much slower than the throughput of currently PCIe and InfiniBand. The HW is another FPGA-based lossy compressor based on ZP, but it is not area bounded. Then I will talk about the motivation and the challenge. So the figure shows the process of building Huffman tree. It needs 7 steps to finish. The Huffman coding has high overhead in terms of latency, area, and the power. And besides, it is hard to build a Huffman tree and generate code words within limited hardware clock cycles to meet the high throughput requirements. And so we decided to use predefined code words at the beginning and update the code words during the runtime. But then it brings another challenges. So how to generate suitable code words to cover the features of one scientific data set. Next, I will talk about the overview of CEAZ. It has three main data flow paths. On the top data flow path, we pre-process the floating point data using quantization algorithm and generate symbols. We will calculate the standard deviation of the frequency of symbols. According to the standard deviation value, we will decide whether to build a new Huffman tree or not. On the middle data flow path, we directly encode symbols using existing code words for seeking high throughput. On the bottom data flow path, it is fixed ratio mode. We will feedback total bits of encoded symbols to estimate the compression ratio, then adjust the error bound. Then I will talk about the design methodology. I will first talk about the approximate sorting. As shown in the figure, frequency of symbols are generated by Lorenzo predictor, and the linear scaling quantization are symmetric. Besides, the Huffman encoding are relatively robust. So we choose the approximate sorting to save time. The main idea is that we just compare two frequencies of symbols in the left and right of the middle symbol and store them in a correct order into the output. The experiment shows that our approximate sort save the sorting time by 7.5 times on average over the magic sort. Next, I will talk about the offline Huffman codewords generation. The main goal of this step is to make the offline codewords representative. We will generate the different offline codewords for different types of dataset. Currently, the types of offline codewords includes climate, cosmology, molecular, and physics. When we encounter a new types dataset, we will first use the average offline codewords. Then we will add the offline codewords of this new type into our offline codewords repository for future use. We use 4 steps to generate offline codewords. Firstly, we set a suitable error bound to let our compressor has the similar compression ratio on different dataset under the same type. Second, we will collect the symbol frequency on different datasets using under the same type. Third, we will calculate the average symbol frequency from the collected frequencies. The average symbol frequency are used to generate offline codewords. Finally, we stored the offline codewords of this type into our offline codewords repository. Then I will talk about the fixed compression ratio mode. In this step, we need to estimate the bit rate of symbols after Huffman encoding. After we get the bit rate, we can calculate the compression ratio. High bit rate means low compression ratio. So give a code word SI, its length is LSI, its probability is PSI. So we want to get the average bit length. So we do it by summation over the multiplication of code words, probability, and its length. Then when we double the error bound to 2 times EB, the symbols histogram also shrinks accordingly, where the total number of symbols is reduced by 2 times, and the probability of each symbol is increased by 2 times. So in this case, the bit rate should be represented in this equation. So B prime is the bit rate of 2 times error bound. B prime is equal to B minus 1. B is the bit rate of 1 times error bound. So we can conclude that when we double the error bound, the bit rate should increase by 1. And we will use this policy to adjust the error bound to make sure we can reach a targeted compression ratio. Then I will talk about the policy of updating code words. When we frequently update the code words, it is benefits is that we may get a high compression ratio since updated code words is close to the optimal code words, but it may decrease the throughput. Besides, we also need more space to store the code words. The symbol generated by the dual quantization present a centralized and a symmetric distribution. The generated code words is highly related to the distribution of symbol frequency. Those good characteristics inspired us to evaluate the similarity of 2 sets of symbol frequencies use STD, especially assume sigma 0 is the STD obtained from the previous data chunk. Sigma 1 is the STD obtained from current data chunk. C is equal to absolute sigma 0 minus sigma 1. We defined a set of threshold and following the following strategy to update the code words. So firstly, we will not generate new code words if C is less than tau 0, because when 2 frequency with the similar distribution, the generated code words almost identical, then we will generate new code words if C is larger than tau 0 and smaller than tau 1. We will use the offline code words if C is larger than tau 1. Also, as shown in the figure, our experiments shows this trend. The larger change of the STD, the higher compression ratio drop. Then I will talk about our how to integrate CEAZ into the system. So figure shows the overview of our system architecture integrated with CEAZ compression engine. Our system includes 2 parts. The host partitions the input dataset and feed the chunked data through the PCIe. The raw data is buffered in high bandwidth memory with 460 GB per second bandwidth, and convert it into streaming data by memory to stream unit. The compression engine will compress the streaming data in real time and output the compressed data. We also propose apply CEAZ to the future HPC system as shown in the figure, especially CEAZ directly integrate to the FPGA-based SmartNIC. So each computing node are used to compress the raw data before transmitted it to storage via interconnection network. There are two main scenarios to use CEAZ compressed data in the storage. The first one is checkpoint for the restore. The second one is use the to post analysis and the visualization. Thus, there is no need to change the storage system to adopt our design. Then I'll talk about the experience setup. So the first platform is Xilinx Avio 280 data center accelerator card. It has 8 GB HBM2 and 32 GB onboard DDR4 DRAM. The second platform is Summit supercomputer for IO simulation. We will measure the compression time and the transmission time of compressed data to calculate the speed up. The third platform is NVIDIA Tesla V100 GPU for comparison with cuSZ and cuZP. To conduct our evaluation and comparison under realistic scenario, we use 6 real-world dataset from scientific data reduction benchmark as shown in table. So our dataset includes climate, cosmology, molecular, physical, and Brown. Then I will show CEAZ compression ratio. The yellow bar is for CPUSC. The blue bar is for our CEAZ. The red bar is for birthday. So compared to the birthday, CEAZ can provide 1.8 times to 16.4 times high compression ratio. And compared to the CPUSC, our degradation of compression ratio is within 23%. So then I'll talk about PSR. PSNR is widely used indicator to assess the distortion of data of the lossy compression. So the degradation of PSNR of our CEAZ is within 4 dB. Besides, all the PSNR is higher than 60 dB. We also compared the CEAZ with other lossless compressor such as the LZ4 and the GZIP, as shown in the table. So the CEAZ can obviously increase the compression ratio and the throughput. Then I will talk about the comparison, the compression ratio, throughput, and comparison with GPU compressor. So the throughput of CEAZ is about two times higher than birthday on average. And besides, the CEAZ can also reach 50% to 70% of cuSZ and cuZP's throughput. So the reason why we cannot overpass the GPU compressor is that the GPU has higher bandwidth. It is up to 900 gigabyte per second, and besides, it has higher frequency, which is over 1 gigabyte hertz. So mostly the GPU has higher peak performance than the FPGA. So this is the reason why we cannot overpass the GPU-based compressor. So then I will talk about our robustness of CEAZ. So there are 2 scenarios that the codewords will change drastically. So the first one is at the beginning, the offline codewords may be largely different with the actual codewords. And the second one is during the compression and the statistic of input data chunk suddenly change. So to evaluate the response, so we concatenate 2 different data sets with different type. So as shown in the figure, our response time is within 3.5 milliseconds. Then I will talk about the fixed ratio mode. So we set the target compression ratio of 10.5 and 21 for the single and double floating point data, respectively. So as shown in the figure, that the difference between the target compression ratio and the actual compression ratio is within 7.5%. So this is so the difference is acceptable in our user case. Then I will talk about the scalability with multiple pipelines. So as shown in the figure, so we increase the compression pipeline from 1 to 64. So and as shown in the figure, the throughput in log scale increase linear as the number of pipeline increase. And there are two reasons why we have such good scalability. The first one is because we use Xilinx AVO data center card. It has HBM2, which is high bandwidth memory, and its memory bandwidth is up to 460 GB per second. And besides, we adopted due quantization to totally remove data dependency. Then I will talk about the scalability with multiple nodes. So we evaluated the performance improvements of MPI-IO, that is MPI-PHY write, and the MPI collective operation, that is MPI gather. Again, from CEAZ, we conduct our experiments with up to 128 nodes. So one process per node. Each node holds a copy of dataset for compression and transmission. So the compression ratio on the different error band is shown in the table. So as shown in the figure, the CEAZ supported MPI-PHY rate can improve the overall throughput by 18 times and 28 times on NICs and S3D dataset respectively. And besides, so the CEAZ supported MPI gather can improve the overall throughput by 21 times and 37 times on one NIC and on NICs and SMD. Then I will talk about the conclusion and the future work. So CEAZ is a hardware algorithm co-design of efficient and adaptive lossy compressor for scientific data. So it can adaptively update the Huffman codewords. So it can also accurately control the compression ratio. So in the future work, we plan to deploy our system to FPGA-based cluster like FPGAs, junction cluster. And we also want to extend the CEAZ to DPU-based system. Yeah. So this is all my presentation. Thank you again.